Good evening, everyone. Welcome to the third problem solving session of the course Computational Continuum Mechanics. I'm Naresh, a research scholar in the Department of Civil Engineering at IISc. So today the topic is tensor calculus. The problems for assignment 3 are based on tensor calculus. So we have a set of problems that we started off in the last session, but we couldn't finish it. So we'll start solving these problems and a few others in tensor calculus. Before that, there are a few doubts in the participants. So let me clarify them. So first one is some clarifications. So, your question is this: the relationship between traction, which is a vector, and stress, which is a tensor. And why do we need, given a surface, traction is a vector on that. Your question was, do we need stress to represent the traction vector on a particular surface? Is that's your?
Yeah.
So, it starts off like this. So given a three-dimensional body, there are forces acting everywhere. And suppose this set of forces keeps it in equilibrium. What we do is you take a point, right? So stress is a tensor. So stress, take the Cauchy stress. This is tensor that is defined at a point. So it's a function of x, y, and z at a given instant of time. So at any instant, stress is a function only of a point, which means when you talk about stress, so stress does not depend on surface. Surface, right? So we talk about stress distributions as a function of the volume. But however, traction requires a normal to be defined. Traction depends on surface. Depends on which surface we are looking at. So depends on the surface in question. Let me elaborate further. So from a physics perspective, we only have forces. Right? We only have forces. These forces can be surface forces or body forces. So things like gravity, electrostatic force, which act over a bulk, electromagnetic force, these which act over the bulk of a material are called the body forces. And things like contact forces, friction, these are all surface forces. So the concept of traction is something that is unique to continuum mechanics that doesn't appear in physics. So from a strictly physics-based perspective, we only have forces which can be internal forces or external forces. So uh, if you take a body and cut it here, you just take a body and cut it through a plane. This will expose a surface containing that point. Let us call this point P. And now the point which was in the interior is now on the exterior. So there are forces acting on this body. When the entire set of forces are considered, we assumed it is in equilibrium. But internally, this surface is interacting with the rest of this. So these two surfaces are bonded together. So there are some forces acting between these two, which are keeping the body intact. So these forces are interior forces. Once you make a cut, they are exposed, so they are exterior forces, and these are distributed on the surface of the cut, so they are surface forces. Traction is nothing but surface force intensity. So intensity, as we talk about any other intensity, you take a very small area on the surface. Let me magnify this. You take a very small area element on the surface, call it delta A. It has a set of different forces acting on it. Let that resultant of all these forces be delta F, which is a vector. So traction is defined as the limit of this area tending to 0, the limit of the ratio delta F by delta A. So one of the fundamental hypotheses of continuum mechanics is that this limit exists. So if the limit exists, we can talk about traction. So on all internal surfaces, at every point, we can do this limiting process. You can take very small vanishing areas, find out the net resultant force, which is a vector, and divide it by that infinitesimal area. Take the limit as that area tending to 0. So if this limit exists, you say the traction exists. And one of the fundamental assumptions is this traction vector field exists and it is continuous. So this we call Cauchy hypothesis. So this forms the basis of continuum mechanics. However, if you look at this point here, okay, it's continuous. I could have made the cut in any other direction. So I have chosen to make a cut along this plane. Let us call this plane something, say P x1. No, plane L1. Let us call this plane L1. I could have also made a cut like this, which passes through the same point, but at a different angle. That will expose an entirely different surface like this. Okay? So that will expose an entirely different surface, which also contains the point. However, the normal this internal surface will expose an entirely different set of forces. If you do the limiting process onto this point here, you get a different traction. Say T. Let us call this plane L2. This place L1. So let us call this the traction obtained by using plane L1 is T1, and traction obtained by using plane L2 is T2. If you have to see why these two have to be different, consider just the usual tensor test. Say it is subjected to a net force T. If you take plane L1 like this, assuming it is fairly far away from the plate ends, the traction distribution on that will be uniform with the net intensity T. So it will be something like T by A. A is the area of A1. Now, if you take a plane which is vertical through this point, the resulting body will be like this. And this is subjected to T by 2 here, T by 2 here. On this plane, of course, you will not have any, under the usual assumptions, at this center point, there is no horizontal force. So the traction on this plane, let us call this plane L2, is 0. So on this plane, traction is 0. On this plane, traction is T by A1. So it obviously depends on which surface we are cutting at. So since you can pass before getting to that point. So therefore, traction is not only dependent on the point. So traction at a given point P is a function both of the location of that point as well as the plane which is cutting normal to the plane, right? So a point on the plane already is P. So what else remains to determine the plane? It's only the normal. So traction, you cannot define traction without referring to a point and a normal. So a point and a normal together define a plane passing through that point. So the traction at this point, you cannot define traction at a point. You can only say traction at that point on a plane which contains a normal and to this L1 plane, the normal is E2. Say if you consider a coordinate system like this, 1, 2, 3. And to this L2 plane, the coordinate the normal is minus E1. So traction always depends on this. However, this means that you can pass an infinite number of planes through a point. You can pass an infinite number of planes through every point. Which means if you take this internal force distribution and take the limiting process and find out the traction, there is like, so for N1 you have a traction. For n non-normal, you have traction. You have one traction. For n2, you have traction. But you can have an infinite number of normals at every point, which means you have an infinite number of traction vectors. So this is really hard to handle. This doesn't have any physical. Uh, this doesn't allow any physical interpretation, right? You cannot have infinite amount of information at a given point. Then Cauchy came up with his tetrahedron analysis, which says how these tractions have to be related to each other. So the fundamentals of that is the uh, Newton's laws, Newton's second and third law. So this considers a tetrahedron. This doesn't have to be a tetrahedron essentially. You can take any infinitesimal polyhedron whose area vanishes as the volume is taken to 0, right? So Cauchy considered a tetrahedron with 3 of its faces oriented along the coordinate planes. So if you have 1, 2, 3, and x, 1, 2, 3 axis, you have this plane. This plane has normal minus n3. Sorry, this plane has normal minus e1, e3. This plane has a normal minus e1, and this plane has a normal minus e2. And there is a plane which is facing us that has some general normal n. So as you shrink the volume of this tetrahedron, what happens is on each of these planes you can have a traction. Say on the plane 1, plane with normal e1, you have traction t1. On the plane with normal e2, you have traction t2, and the plane normal to e3, you have traction e3. And suppose you have traction t on the plane with normal n. So these cannot be independent of each other. That was the idea. Because this tetrahedron has to remain in equilibrium. This tetrahedron has to remain in equilibrium under static conditions. You can establish the equations of equilibrium. That is, the sum of all forces in the x direction should be 0. Sum of all forces in the y direction should be 0. And sum of all forces in the z direction should be 0. And as you shrink the tetrahedron to a point, the moments are not really important because a point has no rotational degree of freedom and a point has no dimensions. Therefore, it is sufficient to enforce the force equilibrium equation. You don't need to worry about the moments as you shrink the point as you shrink the tetrahedron to a point. So it is only using these 3 equations, it was proven that the traction on an arbitrary plane n with the normal components n1, n2, n3, this cannot be independent of these 3. So this traction, which has 3 components, say T1, T2, T3, has to be related to the components of this. So this will have components sigma 11, sigma 12, sigma 13. This will have components sigma 21, sigma 22, sigma 23. And this will have components sigma 31, sigma 32, sigma 33. So it is shown that, so now you have a total of say, so you can given, so you have a total of 12 unknowns, right? A total of 12 unknowns at a given point. According to this tetrahedron analysis, you have 12 unknowns. So sigma 9 components of stress and 3 components of traction on any specified n1, n2, n3 plane. So given this, and you have 3 equations of equilibrium, 3 scalar equations of equilibrium. So I can eliminate T1, T2, T3 from this in terms of n1, n2, n3. And if you do the analysis, it turns out that this T1, T2, T3, the components of this vector T is related to the others as sigma 11 n1 plus sigma n12 n2 plus sigma 13 n3 is equal to T1. So it is just that you are eliminating this, you're finding the components of the unknown traction in terms of whatever you assume the components of the stress. So this takes up this form. When you write it in the matrix format, we will get this. N1, N2, N3. And when you condense it in a tensor format, these are the components. So you can express it as the tensor T, sorry, the vector T is a tensor sigma acting on the normal to the plane. So this traction, which is a function of both the point, let me denote the point by x, and the normal to a plane passing through the point depends on the stress tensor at that point, which takes in the normal to the plane and returns the uh, traction on that plane. So here the good thing to note is that we can have infinitely many normals. We can choose this n1, n2, n3 arbitrarily, subject to the condition n1 square plus n2 square plus n3 square should be 1, because it's a unit vector. Subject to this condition, you can have an infinite number of normals at a point, which means you can have infinitely different traction vectors at a point. But that is not easy to handle. So this relationship, which is derived by assuming an infinitesimal tetrahedron and by enforcing the equations of equilibrium onto the tetrahedron and letting the tetrahedron vanish to a point, we get a relationship between the tractions and the tractions on the coordinate planes. So, so this gives us a relationship to find the traction on any specified plane with normal n, given the stress at that point. Now, the stress at a given point is not infinite amount of information, unlike the traction. So this has got only 9 components, and with symmetry, it is only 6 components. So to characterize the internal force intensity at any given point, all that is required is the 6 components of stress. Given the 6 components of stress, you can ask the question of what is the traction on any arbitrary plane passing through that point. So this is a very powerful result in continuum mechanics, in solid mechanics. So that is what it is. So if you just get back to this, if I say the stress at this point referred in this coordinate system is say sigma, no, it is in 2 directions. So it is 0, 0, 0, 0, 0, sigma 0, 0, 0, 0. So I've specified 9 components of stress at this point. Now, if I'm asked the question, if I make a plane, if I cut a plane at this angle at 45 degrees to these two, and it is oriented along, and it is perpendicular to the 1, 2 plane, right? If you cut this along this direction, again, it will expose certain distribution of internal forces, and you can ask the question, what is the internal force intensity at this point on a plane which is halfway between planes 1 and 2, which is at 45 degrees to planes 1 and 2. You can ask that question and you get the result. So for a plane at 45 degrees, the traction, the other alternative is you have to solve this problem as it is, right? We cut this problem as it is, apply a force P here. This has got some distribution. We don't know that. That is what we need to find out. So this has got some traction distribution. At this point, you're interested in the internal force intensity. The other way is you solve the equations of equilibrium and solve this problem fully and then find out this limit. Instead, if you know the stress distribution in a given coordinate system is at 0, 0, 0, 0, sigma 0, 0, 0, 0 at that point, stress at that point, you get this. And the normal, you can get it easily. So for this, the normal, it's a plane at 45 degrees, right? So the normal is like this. So it's actually the other way, no problem. So this normal is, it is what? It is minus 1 by root 2, comma 1 by root 2, right? Comma 0. Z direction, it doesn't have a component. So the traction on this plane is nothing but minus 1 by root 2, 1 by root 2, 0. So this is, so the way I have taken the normal, it is on the bottom half. So if I want on this part, it is, you need a minus sign. So this becomes a plus and minus. So what is this? The traction vector at this point on a plane passing at 45 degrees at this point is, just do the multiplication. First component is 0. Second component is minus sigma by root 2. And the third component is 0. So this means on this, at this point, the force at this point, if this is the distribution on this plane, the force on this plane at this point, the force intensity on this plane at this point is just minus sigma by square root of P and Z. If you take a plane like this, right, you have to recover what we have. So again, you have this 0, 0, 0, 0, sigma 0, 0, 0, 0. this plane has normal in the two direction, right? Here the normal is 0, 1, 0. So let us write it. So it is 0, 1, 0. If you consider this body, the normal is in the downward direction. So let me put a minus sign. So here, this has got components 0, minus sigma 0. So again, consistent with what we would expect, the force intensity at this point through a horizontal plane is minus sigma, which is in the negative y direction. That is what we would expect, because that is what is required to counteract this external force of upward. So this is so given the stress at a point, you can find the traction on any plane passing through the point. That is the idea. So traction depends on normal, whereas stress does not depend on normal. Traction is a vector, stress is a linear map or a tensor. Is that okay?
Yes.
Okay. Yeah. So let us solve. Let us continue solving the problems last session. So if we recollect, we had several. So the last session was on tensor algebra, and some of the relations were. Let's just
Naresh,
have them.
Can I interrupt?
Yes, sure.
For example, in a particular question, the
Yes.
condition is given as that this something is the traction vector. For example,
Okay.
traction vector is there,
Okay.
and we have to calculate the stress tensor on a particular specific plane.
Okay. Okay. We
So
can solve such a
basically,
problem. Yeah.
does it mean that we have to identify the surface normal first, and we have to just distribute the components of tensors along the three perpendicular planes according to that surface?
So uh, why not start with the problem, right? Suppose you are saying the
Okay.
traction on any given uh, plane on through a given plane is so let me put it this way. Let us choose the plane first. Let us choose the plane as, let us say the plane has components 1 E1 plus sorry, 1 by root 3 E1 plus 1 by root 3 E2 plus 1 by root 3 E3. So this is normal, which is equally inclined to all the three coordinate axes.
Yes.
And you said the traction is specified on this plane, is it?
Yeah.
Yeah. So the traction, let us say the traction on this plane is some 20 E1. Yeah. Let us just have it as 20 E1 plus 0 E2 plus 0 E3. Now your question is what? Can we determine the stress? Is it? Can we determine stress tensor? Is it?
Yeah.
Yeah, the answer is no.
Uh,
Because the reason is that if you just write its components in this way, the traction is 20, 0, 0. The stress tensor is some sigma 1, sigma 1, 2, sigma 1, 3, sigma 2, 2, sigma 2, 3, sigma 3, 3. And this part is symmetric. And you have 1 by root 3 by root 3. So this is basically a system of equations, right? So there are, if you expand it out, you will get 20 is equal to sigma 1 plus sigma 1 plus sigma 1 by root 3. So I will put the root 3. 0 is equal to sigma 1 plus sigma 2 plus sigma 2 and you'll get 0 is equal to sigma 1 plus sigma 2 plus sigma 3 assuming 0. So here you have 6 unknowns and 3
yeah.
equations. So this problem is basically not solvable. If at all you need to solve such a problem, you need to know the traction normal. You need to know the traction at least on uh, two two plates. Say two planes, yeah. And it is two planes because we know that the stress is symmetric. If we didn't have stress to be symmetric, we'll have 9 components, so there'll be 9 unknowns, which means you need 9 equations. 9 equations, which corresponds to 3 vector equations. So with one vector equation, we get 3 scalar equations, but there are 9 unknowns. But because of symmetry, it reduces to 6 unknowns. So for example, if I say on the plane N1, T1 is known, and on plane N2, let me call that plane as say, let us just say it is E1, and the traction on that plane is T2, which is say 40 E2. This is allowed, right? This can be solved. Now you can set up the full equation. So you get one is that 20, 0, 0. You have sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 2, 2, sigma 2, 3, sigma 3, 3. You have symmetric sigma 1, 2, sigma 1, 3, sigma 2, 3. Here we have 1 by root 3, 1 by root 3, 1 by root 3. And the other equation we had is 0, 40, we'll say 40, yeah, 40 and 0. Here you have a stress tensor, and here you have the normal 1, 0, 0. And right, 1, 0. Yeah, normal is E1, right? So it is 1, 0, 0. Now, the good thing about the Cauchy relationship is that this T of n at a point x is sigma, which is a function only of x, acting on the normal at a point x. Normal, which so this does not depend on the normal. This is the stress is independent of normal. So at this point, the stresses are the same. So I can just use the same. These components are not going to change. So basically, what I mean is sigma 1, 1. It's the same sigma 1, 1 in the same coordinate system. Now this can be solved. So so this you have 6 unknowns. You have 6 unknowns and 6 equations. So this can be solved. If the equations are proper, they are consistent. If this represents a physically possible combination of tractions, this can be always solved.
Okay, so two planes are required.
Yeah, because the stress tensor is symmetric, you need to find the stress at a point. For given the tractions, you need at least the normals. You need the traction of two. Yeah, you need two vector equations, which is T1 is equal to sigma n1. T2 is equal to sigma n2. So you need two vector equations or 6 scalar equations, which means you need two planes on which the traction is specific.
Yeah. Okay. Okay. Yeah, it's clearly understood for me.
Okay. Okay. Thanks. Okay. So let us proceed to this. Save it. This is a problem. It is this happen. So in the last session, we looked at the concept of a vector. So a vector is a mathematical quantity which exists independent of any coordinate system. For example, you have a particle and you can talk about the displacement vector or the velocity vector, which is some kind of a directed line segment, and it has got components in any specified system of bases. You can specify a coordinate system 1, 2, 3. You can take unit vectors along this coordinate system, call it E1, E2, E3, and you can express any given vector as a linear combination of the basis vectors E1, E2, and E3 in this form. So these scalars multiplying the basis vectors are called the components of the vector referred in the system E1, E2, E3. These are the components of the vector B. The vector exists independent of its components. Therefore, you don't need a coordinate system to describe the displacement of a point. Right? So if a point has displaced by 5 meters towards west, okay, you don't need west because west also is a coordinate direction. So if a point has displaced by 5 meters in a direction that you're pointing out with our fingers, it has displaced by 5 meters in that direction. So you don't really need a coordinate system to describe the displacement. But to do computations on this vector, we need components. So we choose a coordinate system and a basis vector set. So these are called the basis vectors, unit vectors. Directed along the increasing directions of this coordinate axis. We call them basis vectors. And you can always express a given vector as a linear combination of 3 linearly independent basis vectors, or 3 basis vectors. Basis vectors are linearly independent. And the components of that linear combination is called components of the given vector B in the coordinate system V1, E2, E3. So this can be concisely represented as summation I going from 1 to 3, Vi, Ei. And we also saw that as per Einstein's summation convention, the summation sign can be drawn and you can simply write it as Vi, Ei. So whenever you have a repeated index, it means a summation is implied over the range from 1 to the dimension of the space we are looking at. So for example, in 2D, if we are looking at 2-dimensional vectors, the summation will be from 1 to 2. If we are looking at 3-dimensional vectors, the summation will be from 1 to 3. Whenever we have a repeated index, we imply a summation. So this was one thing. Then we looked at what tensor is. So tensor is a linear operator which takes in a vector. So it takes in a vector. Say it takes in a vector u. Think of it as a black box and returns a vector v. So v, if it is v is some function f of u. If this function turns out to be linear, then you can relate v as tu, where t is a tensor. So a tensor is a linear operator which takes in a vector v. It takes in a vector from a given vector space and returns another vector. So by linear, we have also seen what linear is. Linear means superposition rules. So if you have alpha x plus beta y, so f of alpha x plus beta y is nothing but alpha f of x plus beta f of y. So if this holds for all possible scalars alpha and beta and vectors x and y, then we call the operator f to be linear in its arguments. So a linear map from which takes in a vector and returns another vector is a tensor. So a tensor, unlike a vector, has got two indices. For example, if you take the metric system of equations Ax equal to b, this can be in terms of summation. This is a11, a12, and so on up to a(n)(n), x1, x2 up to xn is equal to b1, b2 up to b. So here the summation goes like aij, matrix sum aij xj is equal to bi. So here the summation is over j going from 1 to n, and this holds for all I going from 1 to n. So here this equation holds for all I going from 1 to n, which means on the left hand side and on the right hand side you will have the index I appearing. And the I index is not repeated. So here also you can drop the summation. You can simply write it as aij xj is equal to bj. And the summation is implied as j goes from 1 to n. Why is the summation implied only over j? Because j is a repeated index. Whenever you have a repeated index, summation is implied. And when you have a free index, it means it holds, vi. When you have a free index, it means it holds for every such I going from 1 to n. So this was the concept of free indices and repeated indices. We looked at a special operator called the Kronecker delta, defined as delta ij is equal to 1 if I is equal to j and 0 if I is not equal to j. So whenever so Kronecker delta is also a function of these indices. So if I and j are equal, it takes a value 1, and if I and j are not equal, it takes a value 0. So If you take delta 1, 1, it is equal to 1. If you take delta 3, 2, it is equal to 0 because these two indices are empty. Then we also looked at another special operator called the Levi-Civita symbol or the uh, permutation symbol. And this one has got three indices, epsilon, I, j, k. And this can take values 1, -1, and 0, depending on what these three indices are. So if any of the two indices are repeated, if any of the two indices I, j, and k are repeated, then it takes a value 0 if anything is repeated. So now we have excluded all cases which can be repeated. So there are only two, in a distinct order, there are only two possibilities. So you put a circle, 1, 1, 2, 1, 3. So you can have either 1, 2, 3, 2, 3, 1, 3, 1, 2, which are called 1, 2, 3, 2, 3, 1, 3, 1, 2, which are called uh, uh, even permutations. So these are all these are obtained by not reversing the order of traverse. And you can also have a reverse of this 3, 2, 1, 1, 3, 2, and 2, 1, 3. So these are even permutations and these are odd permutations. So so for these permutations, when you have ijk as 1, 2, 3, 2, 3, 1, or 3, 1, 2, it takes a value 1. And if ijk is 3, 2, 1, 1, 3, 2, or 2, 1, 3, it takes a value -1. And there's a beautiful relationship between the permutation symbol and the Kronecker delta. So if you have epsilon ijk, epsilon ipq, it is related to the permutation symbol as delta jp, delta kq minus delta jq, delta kp. So this relation is very useful in proving certain identities involving tensors. So this is one set of things. Then we also looked at some of the properties of tensors. So tensor acts on a vector to give another vector. A tensor can act on another tensor can act on the same vector to give some other vector W. So A plus B is defined as a sum of tensors A and B. If A plus B acting on U gives AU plus BU for all, which is basically B plus W. So so this A plus B can be called as C. So you say C is equal to A plus B if CU is equal to AU plus BU for all U. This is how we define the sum of two tensors. We also define the product of two tensors. It is AB of U is nothing but A acting on BU. So this BU can be another vector V, and this is AV. So if so C is called the product of tensors A and B if for every U we have CU is equal to AV where V is equal to BU. So this is product of two tensors. Then we looked at the gradient and yeah, so this part you can start off here for the gradient of a vector. Just get to yes. Okay, so this is basically week 3's content. The first idea is differentiation of tensors. Uh, so you know from basic calculus that if limit for scalars, right? For scalars, we know very well what differentiation means. So we say something as uh, suppose you have a function f of t, right? And we define something as df by dt as follows. It is the limit of t tending to 0, f of, sorry, delta t tending to 0, f of t plus delta t minus f of t by delta t. In other words, without the idea of the limit, you can also say f of t plus delta t using the Taylor series is f of t plus a certain quantity. We'll see what that certain quantity is. Certain quantity multiplied by delta t plus certain other quantity multiplied by delta t square and so on. Now you further write this as f of t plus a certain quantity multiplied by delta t plus a large number of terms which all have delta t square in common because the other terms are delta t cube and so on, right? So you can take delta t square commonly. Now divide the entire expression. So here delta t is not 0. It is delta t is greater than 0. Yeah, we have still not taken the limit. Now we can divide throughout by delta t and take it to the other side, which means f of t plus delta t is equal to now f of t plus delta t minus f of t divided by delta t is equal to this certain quantity plus you have a large number of terms multiplied by delta t. Now you take the limit delta t tending to 0. What happens? You get f of t plus delta t minus f of t by delta t is equal to a certain quantity that does not depend on delta t. So this quantity does not depend on delta t plus limit delta t tending to 0. You have a certain constant multiplied by delta t. This limit is easy to evaluate because you have delta t here. This vanishes. So this is a constant. This depends on delta t, right? So here you'll have higher order terms in delta t. This will vanish. This does not depend on delta t. So if such a quantity exists, then you call this as the derivative. So this whatever quantity is there such that this limit is independent of delta t and it exists, that quantity is called the derivative of f at the point. So this is in the context of scalars. We can also extend this definition to tensors. How do you do that? So we define d. So this we call as an operator d, which is analogous to d by dt in scalars, of a function of a scalar valued function of the vector t is limit delta t tending to 0 g of t plus delta t minus g of t by delta t. So that is basically this. So df by dt is the quantity such that f of delta t minus f of t by delta t can be expressed as a sum of this plus certain other terms which vanish faster than delta t. So as you shrink delta t to approach 0, these terms will vanish, whereas this will not. So that is how we define this derivative, right? So you take this definition. Now this analogously, you can also write this as have the delta t as it is. So let us write as limit delta t going to 0, g of t plus, put a small value epsilon delta t minus g of t plus 0 times delta t divided by uh, delta t, right? So and you can so, so So basically, delta t tends to 0, which means you can transfer you can put this epsilon on here also. So if delta t tends to 0, you can also say epsilon delta t tends to 0. But if you look at this, we expect this quantity to vanish, right? So this has to vanish. This can happen either by delta t tending to 0 as in the first definition, or as epsilon tends to 0 in the second definition. So I can write this as limit epsilon tends to 0, g of t plus epsilon delta t minus g of t plus 0 delta t by epsilon delta t. This doesn't change anything. Basically, uh, you can write this as you want delta t to vanish, or rather, like you can instead, okay, to make it less confusing, I'll do it. So this suppose delta t is some epsilon times h. So you can write this as limit epsilon h tending to 0, g of t plus epsilon h minus g of t divided by epsilon h. But what is this? This is nothing but limit epsilon tending to 0, g of t plus epsilon h. So as epsilon tends to 0, epsilon h vanishes, minus g of t plus 0h. So 0h is nothing but 0 divided by epsilon h. But what is this by definition? This by definition, you can think of it as you are taking the derivative of g of t plus epsilon h at epsilon equal to 0. Right? So it's nothing but so by this, so you can define this g of t plus epsilon h as some g tilde of epsilon, right? So here the function, so g has the arguments t, right? G tilde has the argument epsilon. So for a given t and h, this quantity is a function only of epsilon. If you fix t, if you fix the point at which you're finding the dg of t, this is a function only of epsilon. So I can do this process. You can define another function which depends only on epsilon. And by definition, what is this? Epsilon, this it is nothing but g tilde of epsilon minus g tilde of 0 divided by epsilon. So this is basically what? It is nothing but limit okay, now we can remove the limit. Limit can be taken inside. So it is nothing but d by d epsilon of g of t plus epsilon h divided by h at epsilon tending to epsilon equal to 0. Right. So the reason we did this formalism from for the derivative at a given point is that this can be easily generalized to scalar vector and tensor functions. So let us do that. Suppose you have a you have a function g which takes vector inputs. So g of so g is a function of vector x. Now we are interested in finding some derivatives. Suppose we are interested in finding derivatives of this. Let us write it down. So by the basic high school definition, we start with perturbing this g to something else. So let us call g. Let us look at g of x plus u. Right. So this g of x plus u can be written as g of x plus a certain quantity times u plus terms with higher order of u. So this O of u means this vanishes faster than u. So x is a vector. So whatever you add to it, so think of it like this: you have the entire xy plane. On this plane, suppose you have points which are determined by their position vector. And for corresponding to every point, you have a certain function g of x. So that function can be some 3D surface, it can be some surface like this. So this can be g of u. If it's a scalar function of a vector variable, it is some. Now we are interested in finding derivatives of this vector valued function. Sorry, this vector function, which it takes in a vector and returns a scalar, right? So we are looking at derivatives of this function. How do you find derivatives? You take a point x. At that point, you slightly vary the this. So from x, you go to another point u, x plus, which is this. Now look at the function value at that point. So this is g of x. This is g of x plus u. Connect these two by a certain by a line or whatever. Now this difference is proportional to this difference has a certain dependence on this u, but there are terms that are of the order u, which means if you divide it by the magnitude of u, and let that magnitude of u tend to 0, this will remain constant. And you have terms which vanish faster than when u goes to 0. So as you bring these 2 points closer and closer, as you take u up, as you approach u to 0, there are terms that vanish faster than. So there are certain terms that will vanish faster than u. So u goes to 0 at a certain rate. U square goes to 0 faster than u, right? Similarly, in the context of vectors, you have two points. You're letting the second point approach the first point. As it approaches, u goes to 0 in a linear fashion. But there are terms in this which go to 0 faster than u going to 0. You club all those terms together and call it O of u. And the remaining part has a certain thing that depends, uh, that is linearly dependent on u. This quantity is called the directional derivative. If it exists, it is called the directional derivative of the function g at, so this is important, directional derivative of the function g at the point x in the direction u, right? So again, using Taylor series, what it is, you can write g of x plus u is g of x plus directional derivative of the function g in the direction u at the point x acting on the vector u, which is the direction, plus terms of higher ordering. Now these terms will vanish faster. They are higher order. Higher order means they go to 0 faster than u itself. Now this by definition is the directional derivative. Now if you look at the first, so this directional derivative is a fundamental concept that is very important for linearization. We'll see how to do it. So let me just so the first question of assignment 3 is based on the concept of linearization. So I will not solve that problem, but I'll solve something similar so that it helps you solve the problems, right? So yes. So okay, it's not fine. Okay, then I can solve any problem. So consider the function. uh, Consider the function g of x as x dot product with x. So if you write it in terms of component, what it is, g of x1, x2, x3, it is uh, x1 square plus x2 square plus x3 square. Okay, this is the function in the components form, and this is in the abstract vectorial form. Now let us suppose we are interested in the linearization of g, linearization of the function g. What is linearization? Linearization is the best linear approximation to any function. So any nonlinear function, given it has continuous first derivatives, can be linearized. Say you have y is equal to x square. And y is equal to x square is a function like this. It is not a linear function. It's not a straight line. But given any point on this, you can construct a linear approximation. And that linear approximation is the best linear approximation to this function. Suppose you say at x equal to 1. So say linearize y is equal to x square about the point x equal to 1. So for linearization, it is important to specify about which point we need to linearize. Now it's an aside. So you have the function like this, which is highly nonlinear. And this is the point x is equal to 1. So this is given y is equal to x square, this point is 1, 1. So it is 1 and 1 square. So it is 1, 1. So linearization of the function y is equal to x square about this point x equal to 1 or 1, 1 is what we wish to construct. So zoom in further here, right? So you have a nonlinear function like this, and you want a linear approximation to this function. What can we immediately think of? What we immediately think of is the value of this function at this point should be equal to the value of the linear approximation. Fine, which means the straight line has to pass through this point. So if you look at a straight line y equal to mx plus c, we want it to be 1 equal to m plus c. That is one thing. But this gives, there are two unknowns which you can choose, right? To get the best linear approximation, you can let the function to have the value at that, and you can also force the derivatives to be same. So you can say dy by dx at this point has to be equal to f dash of x, right? So what is f dash of x? It is 2x. So at this point it is, you can only enforce it at one point. At this point it is 2. So dy by dx at x equal to 1 is equal to 2 into 1, which is 2. Which now apply, so this you can call as the linearization of this. So let us call this y tilde. So dy tilde of x also should be 1, which means m should be equal to 2. Which means you can say c is equal to minus 1. You just so this is 2, so c is equal to minus 1. So what is the linearization y tilde we get? Y tilde is equal to 2x minus 1. Now here x is measured about, so this x is the total this thing. We can let it, so let us see, yeah. So you can write this as 2 into x minus 1 plus 1, right? So y tilde is nothing but 2 into x minus 1 plus 1. Now what do you get? This is so this can take this 1 to the left hand side. So you get y tilde minus 1 is 2 into x minus 1 plus something else. And the something else is 0 in this case. So since this is this is fine. So this is y tilde. What about y? Y is equal to x square. So y minus 1 is y minus 1 is x square minus 1, which is nothing but x plus 1 into x minus 1. So this is f of x. So you're linearizing it about the point x equal to 1. So you can call another variable, you can call this x minus 1 as another variable h. And this you can call it as some delta y. So this is also delta y. So you say delta y in this case about the point x equal to 1. For the actual function, it is in the vicinity of it, it is 2 into x minus 1. X minus 1 is h. And delta y tilde, what it is, that is also 2 into h. But what is the difference? Here y minus 1 is a nonlinear function in x, and here y tilde minus 1 is a linear function in x. So as h, if you double h, y tilde minus 1. So delta y doubles. Sorry. If you double h, delta y tilde doubles. But if you double h here, delta y does not double. So you have got an approximation to this function in the neighborhood of this point. You have got a linear approximation to this function in the neighborhood of this point using the tangent information. Therefore, so a linearization of y equal to x square above the point x equal to 1 is what? It is y is equal to 1 plus what did we get? Y is equal to 1 plus 2 into x minus 1. So this is a linearization of this function. Now, as you take points that are very close to 1, as x is very close to 1, this approaches y is equal to 1 plus x plus 1 into x minus 1, right? So if x is very close to 1, if x is very close to 1, say 0.9999 or 1.0001, then these two functions are very, they are almost the same. But as you take values which are far away from 1, say if you take x equal to 2, what happens? Y tilde takes the value 1 plus 2 into x minus 1, what it is? It is 3. And y takes the value. So y tilde of 2 is 3. And y of 2 is 4. And what about y tilde of 3? It is 5. Whereas y of 3 is 9. So as you go away from this, it may not match. But if you take if you take x as 0.9, for example, or let's say 1.1, which is very close to 1, there y tilde takes the value. So this is x minus 1, 0.1, 0.1, y tilde takes the value 1.2, and y takes the value. So this will be 0.1. This will be 1.2. So it will be 0.12. So this will take the value. That is, this is 0.1 multiplied by 2.1. Sorry, this takes 1.1 plus 1 is 2.1. And this takes the value 1.21. So when x is very close to this point, the linear approximation is very good. So you are approximating 1.21 by 1.2 in the vicinity of x equal to 1. But as you take values that are far away from x equal to 1, say x is equal to 2 or 3, the difference between y tilde and y increases. So this is the idea of linearization. Now we are looking at linearization of this function g of x given as the dot product of x with itself about the point, about which point? Let us take about the point x equal to 0. About the vector x equal to 0. Again, think of it this way. You're having a lot of again, look at it in a planar view. So this is the xy plane, and assume the for now, let us assume the vectors are 2D. So you have a point x, and you have a lot of points. So this is the point 0, and this is the point x. So corresponding to every point, you have a certain surface. So this surface is g of x, which is x dot x. Now we are looking to get a linear approximation to this function about the point x equal to 0. So let us do that. So there are many ways to do it. Let us do it one by one. So you call this as g of x as g of x is equal to g of 0 plus some h times. Let us say x is in the direction v. Let us say this is the unit vector in the direction of x. You can call it as the magnitude times the unit vector. What is this? This is hu dot hu. Now this is a scalar. This is also a scalar. Sorry, h is a scalar. This is a scalar. So you can dot take the scalars out. You get h square times u dot. So this is nothing but g of x, where x is hu. Now we want to express this as a certain. So you want to express g of 0 plus hu as g of 0 plus something that depends linearly on u plus terms that are something that depends linearly on x, something that depends linearly on x plus terms that are of the order h squared. So these will have a h square everywhere, and those will vanish. So let us write it down. So g of x is equal to what is g of 0? So g of 0 is 0 dot 0, which is 0, right? Plus something that depends directly on uh, x plus terms of the order h square. So plus you can have h square u dot u is just 1. So this is just 1. So note that there is no h term. There's no term of the order h, which means this coefficient is actually 0. This is basically g of x, right? This is g of x. So these two cancel out. And you get this term, which is actually the directional derivative of g at the point 0 in the direction u is actually 0. So for this function g of x equal given as x dot x, the linearization of this function about the point x equal to 0 is just 0. But can we construct a linearization, or can we linearize g about a general point x? Can we do that? That is, for the scalars, right? If you have a function f of x where x is a scalar, at any point you can write it as f of x plus h as f of x plus h times f dash of x plus h square times f double dash of x by 2 factorial and so on. And from all these terms, you can take h square commonly out. You can write it as f double dash of x by 2 factorial plus h times f triple dash of x by 3 factorial and so on. Here you have f of x plus h f dash of x. Now you can write this as f of x plus h minus f of x is equal to h f dash of x plus h square times some f dash of x by 2 factorial and so on. So these terms, so this term is of the order h square. It goes to 0 faster than h. Therefore, this function f of x plus h f dash of x is a linearization of f of x about the point x. So this x is not a fixed point. For any point, the Taylor series gives a way to linearize a scalar function about any given point x, right? Because you get this increasing powers of h, and you can cut it off wherever h square comes, and these terms go to 0 faster than h itself. So this gives a linearization of f of x about any generic point x. So what is the directional derivative by definition? It is nothing but the usual derivative f dash of x. So this is the directional derivative of, so d f at the point x. In which direction? In scalars, there's only one direction, which is the one direction is nothing but f dash of x. So along similar lines, we can linearize g about a general vector x. So g of, to do that, consider g of x plus u, or you take g of x plus hu. So you perturb, this is the point x. You take some direction u, you take this direction u, and move in that direction a quantity of hu. So you get another vector, which is x plus hu. Now, so corresponding to g of x, you have a value here, which is g of x. And corresponding to this point, you have another value, which is g of x plus hu. Now, this difference between g of x plus hu and g of x has a term that is proportional to h, and it also has terms that are higher order in h. Basically, those terms go to 0 faster than h. Can we do what it is? So g of x plus hu is x plus hu dot producted with itself. What is this equal to? This is just, you can distribute it. So dot product is distributed. We get x dot x plus hu dot x plus x dot hu plus hu dot hu. So write it all this separately. What is x dot x? X dot x is nothing but g of x. Plus from this term and this term we can take h commonly out. It is a scalar. H multiplied with u dot x plus x dot u plus h square times u dot u. Now this term goes to 0 faster than h, so drop this term. You get a linearization, say g tilde of x plus hu is nothing but g of x plus h times u dot x is the same as x dot u. So you can write it as 2 times x dot u. So what is, so multiply this h onto u. So hu is nothing but, that's fine. So this is nothing but g of x plus 2x dot hu. Now analyze this. So you have constructed, by dropping the terms that go to 0 faster than h itself, you have constructed a linear approximation to g about the point x. So g of x plus hu is given as g of x plus a term that is proportional to hu. So what is this? This by definition is the directional derivative of the function g at the point x in the direction u. And yeah, so this is the yeah, this is basically the concept of linearization. This entire thing is the directional derivative. Fine. So
Yeah.
yes. You said
No, I'm
something?
not saying anything.
Okay.
No.
This is clear, right? So whenever you want to construct a linear approximation or linearize any nonlinear function, use the definition of the directional derivative. So you get the linearization of any function about a given point is the function value at that point plus a term that depends linearly on the perturbation. So this quantity is the directional derivative, and you can, it's also known as the Gauss derivative. So then you linearize something. Again, so the linearization of a function, say linearization denoted by L, of a function f about a point x, right, that is equal to, so say f of x is some general function. The linearization of f is another function. And if you're linearizing it about a point x naught, say linearization of function about a point x naught is nothing but f of x naught plus the directional derivative of this function at the point x naught in the direction x minus x. Right? This directional derivative is in the direction x minus x. So this by definition is the this is the directional derivative. Now you can generalize it further. So the directional derivative of a given function f in the direction u at a given point x is, we have seen, it depends linearly on u. Right? The u appears here, so it depends linearly on u. It is equal to a certain certain quantity. You have a certain quantity acting on u. So if you double u, the directional, if you multiply u, if you say u1, you have the vector, you have the direction u1, and you find the direction derivative in that direction. You have u2, and you find the direction derivative. You add u1 plus u2 is another direction. In that direction, the directional derivatives will be du1 f of x plus du2 f of x. So the directional derivative is linear in the direction itself, and whatever operator here that takes in the direction and returns the value of directional derivative in that point is called gradient of. So again, so this is denoted by the symbol. This is also known as the Frechet derivative. So if there is a linear map, if there is a linear function acting on a given vector and it returns the directional derivative in that direction, such a function is called the gradient of the given function. So again, with an example, if you say, now let's take a different example. I can take f of x as f of capital X is say the length of a vector. So given this, so this can be written as x1 square plus x2 square plus x3 square square root under square. So this is the length of a vector in 3D. Now can we linearize this? Right? So if we what is the direction? So you can think of a directional derivative of this function in a specified direction u. Suppose u is a specified direction. What is the directional derivative? It is you perturb the vector in that direction, write it as f of x plus hu is equal to f of x plus h times directional derivative of f in the direction u at the point x plus terms that vanish faster than h. So drop this, you can drop this. Now let us construct this. What is this? This is basically magnitude of x plus hu is equal to magnitude of x plus h times directional derivative of u, directional derivative of fx, the direction u. Can we simplify this further? Yes. So you can write this as what? So this you can write this as square root of x dot x plus hu. This you can write it as square root of x dot x plus h times directional derivative of u, directional derivative of f of x in the direction u. And now expand this, you get square root of x dot x plus, we have already done this. This is 2 h x dot u plus h square times u dot u. This is equal to square root of x dot x plus h u f of x plus terms of higher order. Now let us use the binomial theorem here, right? So let us take this x dot x out of the square root. So you get square root of x dot x, you take it commonly out. So you get square root of 1 plus 2 times h x dot u divided by this thing, x dot x. There's no square root because it's there. Plus h square times u dot u by h square times u dot u by x dot x. This is equal to square root of x dot x plus directional derivative of f of x in the direction u multiplied by h plus terms of higher order. Now use the binomial theorem here. This is 1 plus, call this. So when h is small, and h is small. These are much less than 1. You can take h sufficiently small so that these are less than 1. So call this term as epsilon. So this will become nothing but x dot x multiplied by 1 plus epsilon power half. This is equal to square root of x dot x plus the directional derivative of f in the direction u multiplied by h plus the higher order terms. So what is this? By binomial theorem, you can write it as 1 plus half into n into epsilon plus n into n minus 1 by 2. So this n into n minus 1 is another half by 2 epsilon square and so on. Now note that epsilon is proportional to h, right? So you can take h commonly out. So you get 2 times. So you get h into, so epsilon, what is epsilon? Epsilon is h into 2 x dot u by x dot x plus h u dot u by x dot x. This is basically epsilon. Now h is proportional to epsilon. So these higher order terms are all proportional to h square, right? So these terms can be absorbed into this O of h. So let me write it fully. Sorry, what's this? Plus du f of x h plus order of h. Now these terms are of the same order as this, so these can be absorbed. So this multiply this out, you get x dot x plus half 2h x dot u by x dot x plus h square times epsilon has another this one, right? So you get h square times u dot u by x dot x. This is equal to square root of x dot x plus du f of x h plus order of x. Again, this is also going to 0 faster than h, so this h square, so this can also be absorbed into this. And you can cancel out this square root x dot x on both sides. So you're left with compare these two. So you get du, the directional derivative of f of x in the direction u multiplied by h is equal to, what is this? So this half and 2 gets cancelled. You get h xu by x dot x. So you get h x x dot u by x dot x. Now, when h is not equal to 0, so we are not exactly looking at that point. We are letting h tend approach 0, but not exactly at that. So h can be cancelled on both sides. Therefore, the directional derivative of u, sorry, if you find it uncomfortable, you can take it to the same side. You get h times du f of x minus x dot u by x dot x is equal to 0. This should hold for all h, right? Irrespective of what h is, this should hold. Therefore, the directional derivative of f of x in the direction u is x dot u by x dot x. Note that the directional derivative is linear in the direction u. Suppose you make u as 2u, directional derivative will become 2 times directional derivative. So d2uf is 2 times duf. So this is linear in u. Now what is the other thing? It says the gradient is such a quantity which acts on the direction and returns the directional derivative. So this is a scalar, you agree, right? X dot x is a scalar, x is a vector. So x dot x is nothing but the length of the vector square. So it is nothing but x divided by x square. This is a vector, this acting on u. So du f of x is nothing but this. Now, by definition, the quantity that acts on a direction to return the directional derivative in the specified direction is called the gradient. So the gradient of f of x is x divided by mod x square in this case. So here f of x is mod x, the magnitude of the vector x. Now we can also cross check this using the indicial notation. So the magnitude of a vector in initial notation is square root of x1 square plus x2 square plus x3 square. Now, what is this? This is basically summation xi, I going from 1 to 3. We can drop the summation. So you get square root of xi. Now you are interested in the gradient of this. So gradient in initial notation is what? The gradient of a function in initial notation is dou f by dou xj ej. So the function here is this. Ej is the basis vector. So grad of this is what? It's nothing but dou by dou xj of square root of xi ej. Now you can use chain rule. This is all scalars. When you deal with the integral notation, everything is scalars. So this acts on this. What do we get? We get 1 by 2 square root of xi. So you have differentiated the square root. Now by chain rule, multiply it with whatever is inside that. Dou by dou xj of xi ej. Now I apply the product rule. So we get 1 by 2 square root of xi. Keep the first one constant. You get xi dou xi by dou xj. And next you keep the second one constant. So you get dou xi by dou xj xi ej. So keep okay, there is something wrong, right? So so the first step is fine. So you you use the chain rule. So you get you differentiate with respect to the square. You differentiate the square root function first. So you get 1 by square root of xi, and then differentiate whatever is inside the square root. But as per the initial notation rules, you cannot use a free dummy index more than 2 times. So a dummy index has to appear exactly twice, and a free index has to appear exactly once. So I is already used, so you can use xk, eg. So you know that dummy index is you can just so summation I going from 1 to n xi is nothing but summation k going xk because they are all summed over. The index k actually doesn't matter. That's why it's a dummy index. You can replace the dummy index with anything. So so that you don't use the same index more than twice. So then what do you get? So you get 1 by 2 square root of xi. Use the product rule. You get xk dou xk by dou xj plus dou xk by dou xj xk ej. These two are the same. These are scalars. So you can just write it as 2 times xk dou xk by dou xj. That 2 cancels with this. So you get 1 by square root of xi. This 2 gets cancelled. We get xk dou xk by dou xj ej. What is dou xk by dou xj? So think about it like this. So you have a function f as a function of x1, x2, x3. What is dou x1 by dou x1? It is 1. Dou x2 by, these are the independent variables. The initial variables are all independent. So dou x2 by x1 is 0. So when, so what is dou xi by dou x2? So it is equal to 1 if I is equal to j and 0 if I is not equal to j. So derivative of one independent variable with respect to another independent variable is 0 because they are independent basically. And the derivative of that variable with respect to itself is 1. Partial derivative of that variable with respect to itself is 1. So this can be written as the Kronecker delta delta kj. So you write this as so grad magnitude of x is you get 1 by square root of xi, and here you have xk delta kj ej. So Kronecker delta is equal to 1 if k is equal to j, otherwise it is 0, which means wherever you have k, you can replace it with j. This is basically xj ej by square root of xi. Sorry, it's not a vector. Xi and xi are scalars. Now expand it out. This is nothing but x1 e1 plus x2 e2 plus x3 e3 divided by square root of x1 square plus x2 square plus x3 square. What we have on the denominator is modulus of magnitude of x square. In numerator, it is nothing but, so it is component of x along e1, which is x1 multiplied by the basis vector 1. Component of x along e1, e2 multiplied by e2. So it is nothing but x. So we, using the components and the initial notation also, we have grad x as a grad of the magnitude of x is x by magnitude of x the whole square. And that is precisely the result we got here. That is it. Yeah. So grad of magnitude of x is the vector itself x divided the quotient vector x divided by magnitude of x. So this is just some. This is how we work with directional derivatives and the gradients. Now we can solve some of these problems. These problems. Let us start with the first one. So these are just exercises in initial notation. So this, the first one is or let us start from the last one. The first one is a bit easy. So let's start from E, right? So those are more challenging. So the left-hand side is divergence of grad of phi comma phi psi. So phi is a scalar function, psi is a scalar function. You're taking divergence of grad of phi psi. So what is this divergence of grad operator? So if you recollect, this is nothing but the Laplacian del square phi psi. Okay. So here we can use the initial notation. We don't need to do the abstract gradient here. This is an exercise on initial notation. So let us proceed. Let us proceed systematically. So let us write this as divergence of a certain vector field V, where the vector field V is grad of the product of two scalar functions phi and psi. What is this? This is nothing but the gradient. The calculus definition of gradient we know is partial with partial xi of the function multiplied by the basis vector. Right. This is the gradient operator. Now this is a scalar. This is a scalar. Xi is a scalar. X is a vector, but xi is a scalar. We have taken the vector component onto the basis vector. Now do the product rule here. So you get dou phi by dou xi psi ei plus dou phi by you keep phi constant, dou psi by dou xi ei. So this is the vector field grad of phi psi. Now this is there's a divergence operator. So what is the divergence operator? So the grad operator is ej partial xj operating on something. So what? So if you have an f here, this is f. So here you have the gradient operator. So the gradient of a vector field is ej partial with respect to xj. This operator dot product with v. So this is a scalar. This is a scalar operator. Basis vector is ej. So this is nothing but ej dot product with partial xj vj. So v is nothing but vi ei. So and ei dot ej is delta ij. So in place of I, you can replace j. So you have, okay, let me not skip any steps. So this So this is nothing but partial xj dot product with vi ei, because I cannot reuse j. So this is scalar. This is vi is a scalar. And ei and ej are basis vectors which are independent of this xj. So you can dot product them separately. It is ei dot ej partial vi partial xj. What is ei dot ej? It is delta ij partial vi partial xj. So this is nothing but delta in place of I you replace with j. So partial vj partial xj. Here we do the same thing. So you have so this is nothing but dou phi with respect to xi psi plus dou psi with respect to xi phi. This is the component. This is the ith component multiply ith basis vector. What is grad of this? Grad of this is partial jth component with respect to the jth coordinate. Jth coordinate, right? So this is nothing but dou by dou xj of. This is the this is the ith component. So if you want jth component, in place of I, just replace j. So dou phi by dou xj psi plus dou psi by. So this is yeah, this is j. Dou psi by dou xj. Now use the chain rule and continue further. So the first term becomes dou by
In
dou
the
square.
last in the last line, you have taken the value of v from the above.
Yeah, in
This yeah
this
one
this v
yeah.
is the same as this one.
Okay
So
okay.
this v has some components vi and ei. So I want jth component. So jth component in place of so vi is partial phi with respect to xi psi plus partial psi with respect to xi. So I is a free index here, right? I is a free index. So I can replace everywhere by j or k or m. So I can replace everywhere by j. So vj is this. Now I just have this, use the product rule. So for the first term, you get dou square phi by dou x. You cannot write xj square because in initial there are no powers, right? Dou xj, dou xj,
Yeah.
dou xj, dou xj psi. Plus in the second term, you have dou phi by dou xj, dou psi by dou xj. Plus the third term, you act first on this, then on this. So you get plus dou square psi by dou xj, dou xj. Plus multiplied by phi plus dou psi by dou xj, dou phi by. This is what? This is del dot del p psi. So further, we can simplify this further. These two terms are the same. These two terms are the same. Multiplication is commutative. So you see what you have to prove? You have to prove something like this. So let us go. Let us proceed further systematically. So you get here. You get dou square phi by dou xj psi plus 2 times dou phi by dou xj dou psi by dou xj plus p dou square psi by dou xj. This is the left hand side. So let us call this one. Now look at the right hand side. You have psi dou square phi plus grad phi dot grad psi 2 times grad phi dot grad psi plus psi dou square phi. Sorry, phi dou square psi. Now let us get what this operator is. This operator is del square, which is del dot del of something. Del dot is this is ei. This operator is ei dou by dou xi. This dot product with say ej dou by dou xj. This is component. This is component scalar. So you can say ei dot ej dou by dou xi of dou by dou xj of something. So this is delta ij dou square something dou xi dou xj. In place of I, replace j. So this is nothing but dou square something by dou xj. This is precisely this. So the first term is directly, so we can write this as del dot del phi psi is psi del square phi plus this is 2 plus again here you have del xj del xj. So it is phi del square psi. We already got this one and this one. Now look at this term. What is del phi dot del psi? Del phi dot del psi is dou phi dou xj ej dot product is dou psi dou xk ek. Okay. Again, these A and Gj are independent. You can take dot product of it. So you get delta Kj, dou phi, dou xj, dou psi, dou xk. But delta Kj is 0 if k is not equal to j. So only term that survives is when j is equal to k or k is equal to j. You can say this as xk, xk. Now when it repeats, it means a summation is implied. So you can just replace xk, k with j or m or t. So,
Yeah.
so this dou phi, dou xj, dou psi, dou xj is nothing but the left hand side grad phi dot grad psi. So that is also true. So you start with the left hand side, simplify it to a final scalar expression. Then look at the right hand side. Right hand side also you can simplify it to a final scalar expression and show that the left hand side is equal to this we have done. This I solved in the last, sorry. This we solved in the last session. What else? This is also simple. Yeah, I will. That's little out of time, but it's okay. Since we started a little late, I can take maybe 5 more minutes. We can. Oh, sorry. What did I? These two are actually the same. These two are actually the same problems. Del square phi size means same as this. So these both are solved.
Yeah.
Yeah. These two are the same problems. Okay, so let us this sort. Let's look at the first one. Or yeah, anything we can do. We can do both. It's not going to take much. So let's look at the first, then. So the first one is u cross v dot w cross x. U cross v dot w cross x. Yeah. So again, for the cross product, we have this expression. So cross product, how we usually determine the cross product as E1, E2, E3, U1, U2, U3, V1, V2, V3. And in the last session, I showed that this can be concisely written. So if you'll get terms like E1 times U2 V3 minus U3 V2 plus E2 times U3 V1 minus U1 V3 plus E3 times U1 V2 minus U2 V2. So if you look at the order of these terms, E1, so you have first term 1, 2, 3, that is positive, 2, 3, 1 is positive, 3, 1, 2 is positive. So these are the odd, this 1, 2, 3, all these counterclockwise. So these are all positive. And when you traverse 1, 2, 3 this way, 1, 2, 3 this way, these are all negative terms. So all this 1, 3, 2, 2, 1, 3, 3, 1, 3, 2. So this concisely can be represented by the permutation symbol. So this cross product is usually, so the cross product is, you can write this as epsilon ijk ei. So the first term is 1, 2, 3, right? U, J, V, K. Dot product, you cannot reuse the same because these are all, these ijk is already used 2 times. So use some other symbols, okay, right? Epsilon, PQR, EK, EP, WQ, XR. Now, UJ, VK, WQ, XR, and the epsilons. These are all components. They are all scalars. So I can take them separately. I can write epsilon ijk, epsilon pqr, uj, vk, wq, xr, and you can dot product the vectors ei dot ep. But what is ei dot ep? Ei dot ep is delta ip. So you get epsilon ijk, epsilon pqr, delta ip, uj, vk, wq, etc. Now delta ip replaces I in place of p. So this can be written as epsilon ijk, epsilon iqr, uj, vk, wq, etc. Further, here you use the epsilon delta identity. Okay? So epsilon ijk, epsilon iqr is nothing but delta. So the trick is take corresponding with positive and extremes and inner. So it's like inner outer, inner out, inner outer, outer inner minus outer outer, inner inner. So this you will get it as epsilon jq, sorry, delta jq, delta kr minus delta jr, delta kq, uj, vk, wq, etc. Let me copy this last. Now expand this out. So you get multiply these terms inside. So you get delta gq, delta kr, uj, jq, delta kr, uj, vk, wq, xr minus delta gr, delta kq, uj, vk, wq. So delta jq is 0 if j is not equal to q. Wherever j you have, you can replace it with q. So you get uq. And similarly for delta kr, wherever k is not equal to r, it is 0. So k is equal to r. So you get uk, uq, vk, wq, x, k. So in place of r, you can replace k. You can do it either way. It will end up in the same expression. Minus here in place of j, you replace r, ur. In place of k, you replace q, vq, wq, xr. So this you can write as uq, wq, vk, xk minus ur, xr, vq. What is uq, wq? It's nothing but u1, w1
Dot.
plus u2, w2. Yeah. So it is u dot w, v dot x minus u dot x, v dot. So you can check what we get here. It should be this simple. U dot w, v dot x minus u dot x, v dot w. So that is done. We can also, so this is straightforward, but I think it's there in assignment 3, so we cannot do that. But this we can do. So this left hand side is del cross phi u, right? Let's do that. Yeah, so here the third one is we have curl of, this is a scalar function, u is a vector function. Again, cross product, use the initial notation. Cross product can be written as epsilon ijk ei, or let me, before that, let's write it as this ei dou by dou xi. This operator cross producted with phi, and this vector you can write it as uj, vj. So this cross product again you can write it as epsilon. I is already used, j is already used. So let us use pqr. EP. So first you have to use qth component of the first vector. So ith component of the first vector is dou by dou xi. Qth component will be dou by dou xq. and rth component of second vector. So jth component of second phi is a scalar, so it's something like x square or x cube. No, sorry, not some s square or s cube. And uj is the vector. So phi uj is the jth component. So for the second vector, rth component will be phi ur. So this phi ur. Now, so what is this? So here you can use the product rule. So get epsilon PQR EP dou phi by dou x cube QQ plus phi dou UR. So this is R. So this is R dou UR by dou x cube. Now multiply these terms inside. So you get epsilon PQR EP dou phi by dou x cube UR plus epsilon PQR EP phi dou UR by dou x. So simplify this further. You get so this is what this is. So using the cross product notation, right? So you have EP. This is so let's take R outside and take. So what is grad phi with respect to x cube? So you multiply both sides by e cube. You get this is grad phi, right? You can write grad phi as this. So the qth component of grad phi is what? It is grad partial phi with respect to x cube, right? So this is qth component of grad phi. And this is rth component of the vector u. And here you have phi. Here you have epsilon PQR. Here, this phi is not acted upon by any derivative, and phi doesn't have any index because it is a scalar. You can take phi outside. And then you have epsilon PQR, partial respect to x cube acting on QR. So what is this? You have a basis vector, qth component of one vector, and rth component of the second vector. So this is basically grad phi. This is the cross product definition. So you call this A, call this B. So EP AQ BR is A cross B. So this is grad phi cross B. And here it is, phi is not going to participate. Here del phi, the partial with respect to partial derivative of some function with respect to x cube is the qth component of gradient. So this is nothing but by the definition of cross product. This gradient operator cross this vector u. So this is the curl of this vector. And this is precisely what we have on. So it is grad phi cross u plus phi multiplied with the curl of. So right, that is this. This is also something. So any other doubts, the initial notation or in the calculus or in the linearization?
Naresh, I have one doubt in the directional derivative.
Okay.
In the sir thought in the first problem, no, that is our strain in green strain and Alamani strain. So
Oh,
in that,
okay.
sir,
I
yeah,
have not seen the lectures fully. Can you state the full question so that it's
full question actually the strain is given, green strain is given by L naught minus L,
okay.
L naught minus L,
Okay.
the whole square.
No, green strain is L square minus L naught square by 2. This is what we call as green strain.
But in the lecture, sir has given the whole square. L naught minus L bracket the whole square. It is given actually.
Oh, that is not the green Lagrange strain. Okay, that is okay. What did he say? Divided by something?
You have a 2 L naught square.
No, if he okay, green Lagrange strain. So okay, maybe. So this is not correct to my Maybe it was a typo. Or whatever. It should. This is green Lagrange strain. The difference in squared
Okay.
lengths divided by the original 2 times the different original square length is the.
Okay.
Anyway, that's okay. But
Same
what is this?
doubt I have, that is after next step, no, the whatever you have written in the first line, no, that is
Ah.
considered. Yeah.
Okay, so it's a typo basically.
I'll
So
solve
green
it.
Lagrange strain is defined
Okay.
this way. L square minus L naught square by 2L.
Okay. Fine.
So what is the thing with the directional derivative? Is that with this, what are they doing?
No, that's only that. After substituting in the second equation, if you substitute, then I am getting the wrong answer. But in first, it is getting the correct answer. That's it.
Okay.
Yeah.
Yeah, this is the correct expression for green Lagrange.
Okay.
This is green Lagrange strain in 1D. In 2D, it has a different. 2D, it
Okay.
is x dot x minus something like this, 2 times. Yeah, in 3D, it is vectorial. You can also try that.
Okay.
Any other thoughts?
No.
Okay. Thanks for attending. Thanks for that got delayed, but still thanks for staying back. If you have any doubts, you
Okay.
can post. You can post in the question and answers.
Okay.
Okay.
Yeah,
Yeah.
thanks.
Thank you.
Yeah.
Yeah.